So the integration we've worked on a lot. Really, the only thing in differential equations that we need to practice is how to separate out variables. That's the only technique we need to go on in solving differential equations in our course. There are many, many courses devoted to these problems. So at some point in your future, especially you lucky engineers, are going to run into lots more of them. But lucky for us, we only need one thing, is just how do we separate variables so that we can solve it. So if we looked at this first one here, the technique, like we talked about a little bit last day, is we want to have the equation, one side with respect to y and the other side with respect to x. So this is how I would like to rearrange so that I could solve this. And now I'm ready to take the integral for both sides. So this will become 3y squared over 2 equals negative x cubed over 3 and a constant. So the technique we're practicing again is just working on the separation of variables. I'll just show you how you could solve this one for y, but that's not going to be our focus for today anyways. We're just going to be practicing separating out and then integrating. So if I wanted to separate and solve completely for y, first I could multiply by 2 and divide by 3. So I'd have y squared is negative 2x cubed over 9. And that constant will still be a constant after I multiply. So y would be plus or minus root of negative 2x cubed over 9 plus a constant. Okay, so I'm going to have you guys try and see how you do with this technique where you wanted to separate your variables. So see what you can do on the next two. So I guess the question is, how many of you remember this antiderivative? This here is the cotangent. So I'm prepared to show you how to figure it out if you forgot, you know, and judging by the look on some of your faces, that's probably the case. So how many people actually remember the cotangent's antiderivative? There's a natural log in there, yeah. So here, let me just show you how you get it back, because, you know, you have enough techniques to do this. So did anybody figure out what was the technique they used? Yeah, well, we only have the really one good technique. So here, I'd be saying let u equal, oh, sorry, hang on. I'd say let u equal, so I'm looking for a function and its derivative, and I'll make it sine x, so that du is cos x dx. And the reason I know ahead of time that I want to pick sine is because when I pick sine, that means cos x is on the top like I want it to be. If you pick the wrong one, if you picked cosine for your, if you picked cosine for your function, then you'd have the function on the top, but the derivative's on the bottom here. You wouldn't be able to pull it out like that. Okay, so not the end of the world, but it is costing us precious time as we do this. This will be the integral of dy, and this will be du over u. So I get y equals natural log, absolute value of u, plus a constant. And so to us, that means y equals natural log of the sine of x. pen is sticking, hang on. Sine of x plus a constant. So you can get away with it. You might not remember though, if the question was just given to you as the integral for cotan x, you'd either have to remember that antiderivative or you'd have to split it into cosine over sine and then work through the problem the same way we just did here. So it is on one of those things. There's only that one page on your textbook that you do need to know about, and it is on there. So, you know, probably worth one of those ones worth knowing rather than deriving it every time. Okay, so for the next one, this time when I separate, I'm going to have x dy dx over e to the y plus 1. So I'm going to move the x's to the other side, and I'll end up with dy e to the y plus 1 is 2 over x dx. And then I'll take the antiderivative of both sides here. Kind of running out of space here. Just going to move a few things. Okay. Now, what do you think we should do about the left side here? The right side, hopefully you just pull that out as natural log x. But what should we do with that left side? So at this point, we don't have a technique that can integrate this one. So, but to separate the variables, this is what the separation of variables would have looked like. So we could have just left it there with separation of variables. So perhaps I should have written that down as just separate variables next year. Okay. Because yeah, anyway, we won't run into those sort of complexities when we do it. Clearly there was a mistake there in the choice. So this one, let's see, separate variables and find the general solution. See if you can work on x squared plus 4 dy dx equals xy. Okay, so for me, when I separate these, I would have the y come over here, and then I would take x, sorry, is it frozen again? And then I would have x over x squared plus 4 dx. So if I integrate both sides, I'll have natural log y is, and this one I can do a substitution. If I put a 2 here and a half there, then du is 2x dx. So I end up with 1/2 the integral of du over u. So this becomes natural log of y is 1/2 the natural log of u and some constant. And of course, I'm going to resubstitute that in. So natural log of y is 1/2 the natural log of x squared plus 4. And I don't need the absolute value brackets anymore. And if I was to separate the y and get it outside the natural log, I have to rewrite it as an exponent. So it's going to become y equals e to the 1/2 natural log x squared plus 4 and a constant. So what I can do here is I could move this 1/2 inside. And I'll show you why I'm doing that. Maybe you remember the rule for this. X squared plus 4 to the 1/2. That constant is the same as multiplying by a constant. And the reason I wanted to do that is this is an identity. Does anybody remember what happens when you take an exponential graph and raise it to the natural log? They cancel out because you're doing a function to its inverse there. So this will become y equals some constant x squared plus 4 to the 1/2. So it's some constant times the square root of x squared plus 4. So the other thing we do is we look for a specific solution. We call this one the general solution. That's why there's a constant in it, is it's the solution for all possible curves. We don't know which one it is unless we have more information. So in this example, if we're looking for more information, it's going to come in the fact that they tell us a point that passes through the original equation. We can use that point to solve for the constant. So the process is going to be the same. If it has a slope of that, we're saying dy dx is y over x squared. So my separation of variables in this case will be dy over y is dx over x squared. And integrating, I'll get natural log of y is, so 1 higher, x to the negative 1 over negative 1 plus a constant. So I'll just call that negative 1 over x plus a constant. And then I need to pull the y out of this, so I would have y equals e to the negative 1 over x plus a constant. And we'd rather deal with the constant in front. So that's my general solution. Now I can use the value x equals 1, y equals 3 to figure out what the constant should be. So substituting it in, 3 equals that constant, e to the negative 1 over 1. So 3 will be equal to c times e to the negative 1. So 3 is equal to c divided by e. That means c must be equal to 3 e's. So then I can go and put that constant back into my problem. And I'll get y equals 3e times e to the negative 1 over x. And this e I'm going to put together because it's got the exponent 1. I could rewrite that as 3e to the negative 1 over x plus 1. So this is the specific solution or particular solution to a problem which says the rate of change is given by y over x squared, and there's a point at 1 and 3 on the original graph. Okay. So the difference between particular and a general is the particular one you solve for the constant. You have enough information to figure it out. All right, so think about how you'd separate this and use the initial condition there to figure out where you're going to be when you solve this, separate it and solve this differential equation from top to bottom. Anybody have luck here with this question? Making progress at all? Just being modest, I hope. So I still want to separate my equation, so one part of it deals with y, the other part deals with x. So that's what I've done to get dx and dy. And then I need to move some things around. So this e to the negative x squared, I guess I could put it here just to make it easier for you to see what I'm going to do. I'm going to move it up to the other side. I'm going to take this y down. So I'll have y squared minus 1 over y dy equals negative x e to the x squared dx. So now we're ready to integrate. Oh dear, what are we going to do with the y's?
Separate.
What do you mean by separate?
Y squared over y minus 1 over y.
Yeah. So those I can pull apart. And this I can make a substitution. So I'll need to put in a negative 1/2 to balance things out. And then here I'll have e to the u du. And let's see here. I can take some integrals now. I'll have to carry on up here. So this will be the integral of y minus 1 over y.
Mr. Joyce,
Yep.
I thought it's e to the negative x squared. Oh wait, never mind.
No problem. I've been known to make the odd mistake here and there. Well, at least don't laugh when I say that anymore. Okay, so this will be y squared over 2 minus natural log y equals, and I might as well put back my x squared. Now this is one which would be very difficult to separate, so that's okay. We can still come up with what that constant would have been, and the way we'll do that is by substituting back in. So if I put in y equals 1, I would have 1/2 minus the natural log of 1 equals negative 1/2 e to the 0 plus that constant. So this piece here is gone because it's equal to 0. This piece here is a 1. So what I'll end up with is 1/2 equals negative 1/2 plus the constant. So that constant is equal to 1. And y squared over 2 minus natural log of y equals negative 1/2 e to the x squared plus 1. So that's the specific solution to the one that we had come up with. You won't always be able to make it explicit. However, if I was making predictions for you on your AP exam, if you're asked to, generally you will be able to separate and make it explicit. So here's a question to tie our last lesson from applications back to what we did yesterday on growth and decay. So it says the rate of change in the number of coyotes is directly proportional to 650 minus that number. There are 300 coyotes initially, and 2 years later there are 500. What is the population after 3 years? Now, I mean, obviously there are no hints when it comes to the AP exam, but the wording that you're trying to think of here is directly proportional, and they give you the number. So normally it would have said like just the population, and we would have carried on as it was. But this is 650, and we'll take a look at what's actually happened when we're done. But this should make some sense to you when we actually look back in retrospect. So we'll talk about why this population is the way it is. So we have some data points. There's a 0, 300, and there is a 2, 500. And hearing those words directly proportional, that's what you get from the population is, there's my proportion, and it's directly proportional to this. And here's my rate of change. So all I did was take rate of change, rate of change, that guy, is directly proportional to this guy. So putting those pieces into a differential equation that I can solve. So let me show you then what it'll look like once we solve. We have dn equals k 650 minus n dt. And remember, k is some constant. It might be like 10% or 5. It's just a number, so even though k is in there as a letter, we don't know what that letter is. We know that we can treat it like it wasn't, if it scares you, just replace it with a number like 5 and then put it back as a k when you're done. But if I try to integrate these, okay. Let's see here. Well, oops, sorry, can't integrate yet. Apologies. I have this n, this pesky n right here that I have to move over, so I'm going to have to deal with that before I can do anything, because I haven't separated my variables. So how about... Okay, so I'm going to move this piece here underneath to be the 650 minus n, so that way my variables line up now. So this will be the integral of dn 650 minus n and k dt. So here's this integral here. I'm going to need natural log to do it. We could make a substitution if you're more comfortable, so why don't we try that? We could say let u equal 650 minus n. Then du is negative dn. So I'd have to put a negative to balance it out. And I'll have the integral of 1 over u du equals the integral, and I might as well take k out of there just so it doesn't confuse me because it's a constant. I can pull that constant out. And now I can do the integrals. This will be negative natural log of u equals kt plus some constant. And of course, I will want to solve this one. In my case, it's for a u. It's going to become, let's make this natural log of u is negative kt plus a constant. Just move the negative sign over. And no, you don't have to subtract the constant now because you just add a negative constant, or you'd be, anyway, you don't have to worry about it. Math with constants is fun. It generally never changes unless you're, anyway, multiplying a variable in or something. So this will be e to the negative kt plus c is equal to u. So c e to the negative kt is equal to 650 minus n. And that'll give me a model. I'll have to switch some things around here. The population is 650. Take away c e to the negative kt. And now I have to start working my magic to figure out what values I could use to answer this problem. But I have a model that is going to correctly model this population. Now I just want to show you what this looks like. This is an exponential graph. So an exponential graph normally looks like this. It would go like that. However, this one has been reflected on both axes. So it means it's going to be going not only this way, but it's also going to be going, oops, that's not a very good picture. Let's see here, like that. So if I wanted to show you what this picture would look like roughly, because of those transformations, be something like this. So the reason that this should make more sense from a biological perspective is eventually the resources are exhausted and the coyotes just can't grow anymore because there's not enough food or there's not enough prey or whatever it is, water. If something is in short supply, you just can't keep growing forever. You have problems. So at some point, nature takes over and the coyotes can't keep growing. They're stuck. So unless they, come out with some technological advancements and the coyotes start farming food or something like we did to overcome our problems, then they're stuck. So we're going to substitute in our values here, and our favorite one is at time 0, so let's start there. So that means I'll have, I know the population, the number of coyotes is 300. So then I can figure out that C is equal to 350. Now how could we have predicted that? Remember we talked about how to do some common sense here? We talked about this last day. So I gave you some biological perspective of why 650 makes sense. What do we call 650 for all the math dorks out there? What do we call that? Asymptote. Good, there's lots of dorks here today. So at 650, that's our asymptote where we're stuck. And what is it that's decaying? Well, we initially have 300. There's 350 coyotes that could join this population. That starts to shrink as we reach that asymptote. So that's why we found the number 350 here, is initially 300, a maximum of 650. So 350 is what I'm going to be eroding. I can take 350 new coyotes. After that, nobody else is allowed to join the pack. So my model gets updated to be, I wish I knew how to write so this pen wouldn't. Cursive, yeah, but then when anyways. So now all we have to do is figure out what that growth constant is for K. And we have another point to do that. It's that at 2 there are, what was it, 500? Yeah. So the number of coyotes is 500. I'll start up here. 650, take away 350, e to the negative k times 2. And if I rearrange this now, I'll have negative 150 is negative 350 e to the negative k times 2. So if I divide both sides, and then I need to use a logarithm here to get that exponent down. So the natural log of 150 over 350, you could cut that down to 15 out of 35 pretty quickly, or you could cut it down to, I guess it would be 3 out of 5. But anyways, won't matter, same problem. Equals negative 2k. So that means k is the natural log of 150 over 350 divided by negative 2. And of course, can anyone do that in their head? Yeah, I don't think so. We're going to need to grab a calculator to go and work that out. So let's go back and grab our handy-dandy graphing calculator. Okay, so we've got the natural log of 150 divided by 350, and that whole thing is divided by negative 2. So there's my value for k. If I want to know how many coyotes there will be, I believe it's, was it 3 years? Okay. Then I'm going to substitute it into my model. So in case you can't see it, here's my model down here. I'm going to use time equals to 3 now that I know what that constant is. So this will be 650, take away 350, and e to the, I'll use my answer here. Yep. Oh, sorry, just one sec. And we're on 3 years. 551.8 coyotes.